Welcome back, ladies and gentlemen. I will mention the Leeds Astronomical Society display just around the corner here, or as you come out of the door to the right. The Society has gone to the trouble of putting on an extensive display of their observations and information about the Society, so do have a look at that. So, now I'm delighted to say we actually have a live speaker, and he sounds quite exotic. He's described as an Aussie-Canadian transplant, so he comes from Australia originally. Brad Gibson is the head of physics and maths and director of the E.A. Milne Centre for Astrophysics at the University of Hull, so not that far from here. His work has gained a degree of notoriety, it says here, by defining the Milky Way's galactic habitable zone, which was considered a top 10 news story of the year by National Geographic. I'm not quite sure why that should get notoriety, really. It's not like he's shot a lot of people or done a bank robbery or something. And he's worked on determining the expansion rate of the universe, which is big thing. Well, yeah, big thing if we know that, can determine it. And his team was awarded the Gruber Prize in Cosmology. And he's also been involved in building the world's first liquid mirror telescope observatory. Sounds really interesting. Have a talk about that one day. That sounds exciting. His commitment to widening participation and diversity and improving career prospects of physics students led to his Changing Face of Physics campaign being named best practice in the country by the UK's Equality Challenge unit. And today he's going to talk about stellar winds, givers and takers of life. So I'll hand over to Brad Gibson.
Okay. Thank you, David. As I walked into the approach to the building, I had flashbacks because I thought, I'm pretty sure I've been here before, inside this building. And I went back to my little database, and I guess the last time I was inside this building might have been Leeds Astro Meet 2016. So I think it was November, a good long time ago. I know I've done a couple of things with the Leeds Astronomical Society since then in the intervening years. And I've had the opportunity to do a few things with the BAA as well, did the autumn webinar last year, and was fortunate enough to do one of the Winchester weekends that you talked about, and had an absolutely fabulous time down there, and more than 6 years ago now since I did that. I was told the theme was going to be stellar winds, and you'll have, this afternoon you'll have an actual expert in stellar winds talking about stellar winds, rather than me, who is not an expert in stellar winds. But I tried to give some thought as to how stellar winds influence some of the things that I do work on. So this is an attempt to bring stellar winds into maybe a different environment in the way that, say, Manisha's talk that you just saw went into some of the details of how those winds interact with the surrounding interstellar medium and the shocks that set up, and how you can infer things about not only the host stars that are driving these shocks, but also the surrounding interstellar medium and the properties of the dust in the interstellar medium. So I won't be focusing at that sort of level, but it'll be sort of a broad brush coverage of some different aspects of stellar winds on scales that maybe influence life, but also on much larger scales in terms of shaping galaxies and sculpting galaxies, but all within that theme of stellar winds. Now, I'm not going to spend too long giving a long overview of stellar winds. Stellar winds, it's a very broad subject, and how you label certain things, you could still call them stellar winds. I mean, a supernova is still driving material. You can call that a stellar wind if you like. A star explodes, and things go flying out, and all those chemical elements that we're made of get synthesized inside of those exploding stars. So, a talk about supernova is also a talk about stellar winds, but I'm not really going to talk about supernova, those, the extreme end of the tail of stellar winds. It'll be a little bit more about what happens before those stars explode. And stellar winds apply to, the very high mass stars, which was sort of the focus of Manisha's talk just a few minutes ago. But it also scales all the way down to the lowest mass stars, like the sun. And so you can see that right at the top there. Different stars have different types of winds. And so if I start with something small like the sun, it has a solar wind, a stellar wind. It's not as spectacular and as exciting as some of the ones you saw in Manisha's talk, in the sense that it doesn't drive what we call a bow shock as it plows into the surrounding interstellar medium, that wind. But it is still a wind, and it's a wind driven by that hot atmosphere of the sun, the corona of the sun, millions of degrees, very, very, very hot. That hot corona is able to accelerate the particles that are part of that corona, the electrons, the protons, and some of the heavier chemical elements as well. They get heated up, and that allows them to these extreme temperatures, and that allows them to escape the strong gravitational field of the sun. If you didn't have that super hot corona accelerating those particles, there wouldn't be a solar wind. Those particles would stay bound to the sun because of the sun's gravitational field. And so those high-energy particles are able to escape the corona, and they escape at speeds of several hundred kilometers per second, and it's driven by these millions of Kelvin temperature of this corona. So that is a stellar wind, and we'll come back to that in the particulars of the solar wind and how the solar wind interacts with the surrounding interstellar medium in just a second. It's not quite as spectacular as the bow shocks you would have seen in Manisha's talk. You can move to stars a little bit heavier, a few times heavier than the mass of the sun. They also drive winds. They drive winds while they're on the main sequence, just like our star does. The winds get a little bit more exciting towards the end of the lifetime of those stars that are 2, 3, 5 times heavier than the sun, where you start to puff off the outer atmosphere as it goes through what's called an asymptotic giant branch phase. And so you get these beautiful planetary nebulae that we all love to take pictures of and show people. And that's just one random example of one of these planetary nebulas, NGC 6565. These sorts of stars, at this point in their lifetime, when they're driving these stellar winds, just like some broad brush numbers, they lose about 1 solar mass of that star. So maybe say it's a 5 solar mass star. It would lose 1 of those solar masses every sort of few thousand years or so at the end of its lifetime. I didn't say anything about the mass loss from the sun currently. While the sun is sitting on the main sequence, yes, there are these high-energy particles being accelerated away as part of the solar wind. But in terms of the amount of mass that is, it's inconsequential, tiny, tiny little bits. It's not very much. At the end of its lifetime, when it goes to this sort of phase, yes, it'll start to ramp up and you'll start to get a lot more mass being blown out during that planetary nebula phase. But, for those stars that are few solar masses, that's the sort of number to keep in mind. You're losing about 1 solar mass every 1,000 years or so, right at the end of its lifetime. In this case, when I talked about the sun, the solar wind is being driven by the hot temperature of the corona drives the particles and allows them to escape from the gravitational field of the sun. Here, in this phase of these lower and intermediate mass stars, it's radiation pressure, it's photons that are pushing against dust in the outer atmosphere of the star. These stars are, in the outer atmosphere are rather cool, so you can form dust. And the photons push against that dust and drive it away at speeds of a few kilometers per second. They're not really high speed. These are not supernovae that are blasting out at 10,000 kilometers a second. They're spectacular looking. There's a significant amount of mass coming out every 1,000 years or so, but it's moving at a fairly sedate rate of a few kilometers per second. So those are the intermediate mass stars. If you move to the higher mass stars, and you saw pictures exactly like this in Manisha's talk earlier, these massive O and B type stars, and that's just one particular example, is LL Orionis. It's a 40 solar mass star, so 40 times heavier than the sun. It's losing mass at a much more significant, let's say, speed, let's say. Going at thousands, these winds that are being driven are moving at thousands of kilometers per second. You're losing a solar mass or so towards the, through that lifetime, towards the, every million years or so. So again, intermediate mass stars, they're losing about a solar mass every 1,000 years, but that's compressed really to the death throes of the star. These ones are driving mass loss almost from the time they're born, when they're on the main sequence. So for several million years, they're blowing off about a solar mass every million years or so. And we'll come back to what that material is and what happens to that particular material in just a few minutes. And in that case, the wind is not being driven by photons pushing against dust in the outer atmosphere. These stars are really hot, so they probably don't have a lot of dust. They probably have a little bit, but it's so hot that the dust grains get broken up. And it stays as atoms, if you like, rather than really complex dust particles. But the photons, they push against these particles, in this case, atoms of carbon and nitrogen and other types of heavier elements. And they push on those atoms through, it's called various absorption lines. Now, I'm not going to spend a whole lot of time talking about the massive stars in terms of their interactions with the interstellar medium, those bow shocks that you heard about. For context, maybe what is the size of the sorts of bubbles that get blown? We'll talk about the sun in just a second. There is a bubble. There is a solar bubble. There's not some strong shock out there because it's a pretty minuscule sort of wind that is blowing in the grand scheme of things. But there is a bubble around the sun. And I'll show you in just a second something called the heliopause, the heliosphere. You'll hear different terms. The scale of that is not particularly large. It's on the couple of sort of the smaller than the Oort cloud. So it's well beyond Neptune. I don't know, a couple hundred AU, something like that, is the bubble that is around our sun. These stars that are much heavier, like this one, this is the Bubble Nebula, also NGC 7635. That's a 44 solar mass star that is blowing a much bigger bubble. It's about 2,000 times greater than the bubble, if you like, that's around the sun. So just a bit of context in terms of the size of the sorts of things that we're talking about, because again, the size of these things is going to come into play when I talk about their influence on much larger scales, the scale of galaxies as a whole. So that's sort of the taxonomy of the primary types of winds that I'm going to talk about. So there are 4 points. They're almost sort of mini talks in some sense that I'm going to focus on for the remainder of the talk. I will come back. We'll start locally. We'll look at the solar wind and the heliopause, what that means, how important it is for, say, the development of life. We can step out a little bit further to what we call the local bubble, the local environment, nearby stars, maybe out to the scale of a handful of light years, maybe a little bit further, and how this local bubble is it's an underdense region where you've got multiple bubbles that are pushing up against each other, and how that sculpts and shapes the interstellar medium as a whole. And then I'll build from that to larger scales and talk about galaxies. I'll introduce you to something called the overcooling crisis, which drove galactic physics and the modeling of galaxies for 25 years or so. It was a gigantic mystery. I'll come back to what that overcooling is in just a second, because stellar winds turn out to be, if not the only solution, but probably a primary component to solving this massive problem that plagued the entire extragalactic, or at least the galaxy modeling community, let's say. And then I'll end with a little bit about life and the development of life and the role that stellar winds play. And I'm not going to be talking about supernova again. I could give an entire talk about supernovae and the synthesis of most of the chemical elements that are around us, like iron and titanium, all the heavy elements. They come largely from exploding stars. But there's some interesting things that happen before a star explodes in terms of polluting the interstellar medium with chemical elements that are fundamental to the development of life. And they often get short shrift in some sense because supernovae are a lot more spectacular when they explode, and there's lots of exciting things that you can look at. And so the role that stellar winds play before that explosion phase sort of gets swept under the rug largely. So I want to just lift that rug up a little bit and just show you the role that these stellar winds play in providing the chemical elements for the development of life. Okay, first, that the wimpiest of all the winds, that is the solar wind. And there's millions of different representations of what this looks like. There's the sun, that little yellow dot in the center there. And there is, this spherical bubble around us. Again, doesn't go out particularly far. This is the wind that's it's the high energy particles, the electrons, the protons, some chemical elements that have been accelerated by the corona, moving out at hundreds of kilometers per second out into the interstellar medium. They're constantly slowing down. The interstellar medium, it's all around us, and it provides pressure. It kind of pushes against that. And so you've got this balance of the bubble pushing out, providing pressure, and the surrounding interstellar medium also trying to push back on that. And there's this thing called the termination shock. And that's basically when the speed of the wind, it starts off at a few hundred kilometers per second, but it slows down and it slows down, and it drops below what's called the sound speed of the interstellar medium. That's what we call the termination shock. And there's a much larger, and near the edge of the termination shock, there's all kinds of interesting physics as things get all churned up. The whole thing that sort of surround it is called the heliosphere. The edge of it is called the heliopause. There's a subtle difference between, so what happens at the heliopause, this termination shock is when you could roughly think of it as the speed of the wind dropping from 300 or 400 kilometers per second down to 100 kilometers a second, which is what the speed of sound is around this region. It still slows down even beyond that, and basically becomes indiscernible from the interstellar medium at this place called the heliosphere, and the edge of it's called the heliopause. And the heliopause is not a perfect circle. It's not some big, slightly larger bubble around the termination shock. It looks like a cometary tail. Why does it have that shape? There's lots of different reasons. The sun, it's not standing still in the interstellar medium. It's moving through the interstellar medium. And so you do get a tail that's partially shaped by the motion of the stars that moves through the interstellar medium. The interstellar medium is also threaded with all kinds of interesting magnetic fields. Those magnetic fields shape this heliosphere. And there's an entire cottage industry around trying to understand why that heliosphere has this long cometary shape. And it's a lot of different physical processes that are competing simultaneously that give it that, in this case, looks like a bit like a cigar shape. And it has all kinds of really interesting influences on us, and probably the most important one, and if you've got keen eyes, you will see Voyager 1 and Voyager 2. They passed about 10 years ago or so, that they exited the heliosphere, that influence of the radius of influence of the solar wind, and moved into what we call truly interstellar space, no longer seeing the influence of that heliosphere. And there, as you cross that border from the solar bubble into interstellar space, the detectors sensed exactly what we kind of expected. Inside this heliosphere, inside of this safe bubble, we're actually protected. It's something of a shield. Our interstellar medium, our galaxy is filled with cosmic rays, again, high energy particles. We generate some from the sun that I just talked about, but also exploding stars, all massive stars. There are lots of particles that are moving at very high speed with incredibly high energies. Many of them are charged particles. They can be protons, they can be electrons, they can be heavier particles. Many of them are charged. The vast majority of those charged particles that would otherwise come racing down into the inner part of our solar system and run into us are blocked by this heliosphere, this heliopause. About 90%. Some of the high energy ones do get through, and if they are neutral particles that don't have a positive or a negative charge, they actually pass through as well. So if there were high energy neutrons, high energy neutral particles, they're oblivious to this magnetic shield, if you like. But the vast majority of the high energy cosmic rays that are charged are blocked. And that's good, and I'll come back to it towards the end when I talk a little bit more about the influence on life. But these are the sort of particles which are not conducive for the development of life. As DNA is starting to kickstart, it gets damaged, things get broken apart. These high energy cosmic rays are not a positive in terms of the development of life. So anything that provides a shield, a magnetic shield, to reduce the influence of these cosmic rays and the impact that they would have here on Earth is a positive. So even though this is kind of a wimpy wind in the grand scheme of things, it does play a really important role at the level of blocking about 90% of the high energy particles that would have made maybe the development of life a little, not impossible, but maybe a little bit more challenging, let's say. So that's, a positive in terms of solar winds, and one of the, thinking back to the title, one of the givers of life. If I step out a little bit further, when I move outside that small little bubble around our sun, you start to move into the interstellar medium, but we're not isolated. There are other stars around that are also driving their own bubbles. Some of them are a lot more interesting and a lot more exciting because they're not tiny little wimpy things like the sun, but they're a lot bigger. They're blowing much larger bubbles, kind of like the bubble nebula that I showed you earlier. But at the same time, you've got stars over the last 10, 20, 30 million years that have exploded, have gone supernova in and around this region. When those stars explode, what might have been tiny little bubbles, wind-blown bubbles, can get amplified into much larger bubbles. And you get this complex network of overlapping bubbles that shape what the interstellar medium looks like. And so this is kind of a cartoon diagram of our local solar neighborhood. Here's the sun, and you can see Antares over there. So these bubbles, they do run into each other, they do collide, and maybe Julian in his talk will be talking about colliding winds as well, maybe not exactly in this sort of context, but these bubbles don't evolve in isolation. Stars, are friendly. There's nearby stars, and those bubbles do, and those winds do interact with each other, and all kinds of exciting, super cool physics happens, and then that's what you'll see in Julian's talk. So these winds, like I say, they push the interstellar medium around, not just tiny little bubbles, but they can push them, like the bubble nebula, can make much larger bubbles. And one of the effects of doing that is that it takes, what might have been, you might perceive to be a really smooth interstellar, a smooth gaseous interstellar medium, and it makes it a lot more pockmarked. You get large super bubbles, you get regions that are high density, you get regions that are low density. You're making it more turbulent, you're churning up the interstellar medium with all of these bubbles as they're pushing around. And they're heating up the interstellar medium, making it more turbulent. And if you want to think of it this way, you're loosening it up before stars start to explode as supernova. So when a supernova explodes, if it happens to be in a region that was, stars like to form where there's a lot of gas, where the gas density is high. High mass stars, they live fast, they die young, and they explode. And if they explode in a region where the density of gas is really high, yes, they will blow out a supernova remnant, but it uses up a lot of its energy in trying to move this high density gas around. And so the efficiency of the exploding star contributing to the surrounding interstellar medium gets reduced when they explode in really high density regions. So you won't drive as large a bubble. You won't heat up and make the surrounding interstellar medium as turbulent, because you use up all of your energy pushing your way out of this high density gas. If you take into account the fact that before a star ever explodes, like the bubble nebula, like the sun, you've sort of heated up the gas, you've moved things around a little bit, you've made it more turbulent. There are regions where there is low density and not much around. And so when a star explodes in one of those regions where there's a bubble around, you're able to use a lot more of that energy more efficiently to blow the bubble even larger, because you're blowing it up inside of a low density region rather than a high density region. And this is how you end up sculpting these much larger bubbles that are many, many light years across and parsecs across in some cases, really, really large ones. And this is, I guess for those who like the numbers, if you were wandered around inside this local bubble, the density of the material is around 1/10 of what the average density of the interstellar medium of the Milky Way is. So it's not, zero. It's not like these bubbles are entirely empty. There's still stuff inside of them, but it's about 1/10 of what you would find when you move outside the bubble into the smoother surrounding interstellar medium. Just to have that number in mind. This is really, really important for some of the work that I do in terms of what shapes a galaxy. How do these stellar winds really sculpt what we actually see in nature? And so take a step back and just, a couple minutes on how galaxies form and how galaxies evolve. This is one of the most overused slides in all of astronomy. It sort of captures the evolution of the universe in a single snapshot from the Big Bang over here. You've got, tiny little thing, primordial quantum fluctuations in there. There's a rapid inflationary phase for a few 100,000 years, and those primordial quantum fluctuations that are there get amplified to be these things that we now know and love, these temperature differences. This is the cosmic microwave background. So during that early phase, those first few 100,000 years, the universe is very small, it's very dense, it's very hot. And it's so hot that if hydrogen, the most common element in the universe, what is hydrogen? It's a proton, a positive charge, and it's an electron, it's a negative charge. They like to stick together. Unless you make things really hot and really dense, then all the electrons get pulled off. Same thing with helium. It's got more electrons. You've got 2 electrons instead of 1. But when the universe is really hot and dense, as it was in that first few 100,000 years, you've got the sea of electrons all around you. The universe is very hot. It means there's photons, the same sort of photons that we see today from stars, from galaxies. They're there from the Big Bang, but they can't actually move very far because there's this cloud of electrons around, and they sort of get bounced around and scatter around all the time. It's only as the universe continues to expand, it cools down, then that sea of electrons are able to reconnect back onto protons and become neutral hydrogen, or connect onto helium and become neutral helium. That lifts the veil, and then those photons, the energy from the Big Bang, we see this imprinted on the cosmic microwave background. That's the furthest that we can look back in time, because it's just a fog after that. And those temperature differences, the areas that are red as opposed to the areas that are blue, almost everything that is on there is about minus, in terms of absolute Kelvin temperatures, about 3 degrees Kelvin, or 3 degrees above absolute zero, minus 270 degrees centigrade, if you like that. The temperature differences, if the green is 3 degrees, the red is like 3.0001 degrees, and the blue is 2.9999 degrees. Tiny, tiny little temperature differences. Those tiny little temperature differences are left over from the primordial quantum fluctuations at the beginning. These set the seed for everything that happens thereafter. These tiny little temperature differences are ultimately what drives the formation of galaxies. And we can look at this temperature pattern, or we can look today and look back in time and count the number of galaxies that we see as a function of time, looking backwards. We can use those sort of observational data to figure out exactly what our universe is made of. We can figure out how old it is. We can figure out how much of it is dark energy, how much of it is dark matter, how much of it is the normal stuff that we are made out of. And when you look at all of the observational evidence that is there, we can, let's ignore dark energy and just look at what the matter of the universe, what is it? About 85% of it, the vast majority of the matter in the universe is dark matter. We don't know what it is. Someone will figure it out and they'll get a Nobel Prize for it. But right now, while we can't see it, we can feel it. We can feel it through its influence and gravitational influence. It's actually quite a really simple particle to put inside of a computer because it doesn't care about light. It doesn't care about magnetism. It doesn't care about radioactive decay, all of the other fundamental forces which make things really complex. The only thing it cares about is gravity. Very simple force. And then the other 15% is the stuff we actually see with our eyeballs, with our telescopes. That is the normal or the baryonic matter. What it means is that the vast majority of the universe is made up of stuff that only cares about what we call the inverse square law. And what is the inverse square law? Well, I've got a microphone on, so it's not quite the same, but if I was just talking with my normal voice, David might be 2 meters away from me, and here's a certain decibel. Ram right at the back can, maybe is 10 times further away, let's say. So you might think, well, 10 times further away, the sound is going to be 10 times lower. But no, it's an inverse square law. It means it's 10 times lower. It's 100 times lower in terms of decibels in the back of the room compared to where we are here. Same thing with electricity, magnetism, light. They all obey this inverse square law, just like gravity. The gravitational influence between my two fists right here, there is a certain gravitational influence, but they can feel each other. If I go 10 times further away, the force of gravity between them drops off a factor of 10 times 10, a factor of 100, not a factor of 10. So you can put millions and millions and millions of particles inside of a supercomputer, and you don't have to worry about any of the complex physics. All you care about is the inverse square law that acts between this particle and this particle and this particle and that one and that one and that one. And you can have billions and billions and billions of particles, but the physics is really simple. And that's really good. If you're interested in doing simulations of the universe, large-scale structure, yes, you have to have clever algorithms to do this efficiently inside of a supercomputer, but the physics is no different than what you would have done in GCSEs and A-level physics. There's no complex physics that goes into this whatsoever. And it's great. You can do this. You can take the cosmic microwave background. That can be your initial conditions. This is going to be the seeds for my universe that I'm going to form. So I will use the cosmic microwave background and throw lots of particles in there and just let them interact with each other using the inverse square law. And I can do a gigantic simulation, and I can get something that looks like this spongy web-like structure. And while the comparison maybe doesn't look ideal, if I take observational data and I measure how much of the observational data is in high-density region, how much of it is in filaments, how much of it is empty, what we call voids, statistically, what I see in nature, what I get out of my supercomputer is exactly the same as what I observe. It's really easy to simulate the universe in terms of the physics anyways. There's no complex physics involved, and we get very nice representations of what the universe looks like in a statistical sense, just with the inverse square law. Now, if you wanted to, we live in a spiral galaxy. I'm interested in spiral galaxies. I'd love to be able to do the same thing with spiral galaxies. Some of the first models that were done with computers to try to get spiral galaxies, I can go back sort of 40-odd years or so, Simon White's work, where he took blobs of particles and just threw them at each other in different ways in the hopes of getting, looking at different types of galaxies that might form. Again, using no complex physics, just the inverse square law, nothing more than that. So you throw these two systems at each other, but he always got something that looked like a blob. It always looked like an elliptical. He never got anything that looked like a spiral. There's no spiral arms. There was nothing flattened. Everything just looked like an elliptical galaxy when he used just the inverse square law. And so that's basically where things stood, through the late 70s, through the 80s, through the 90s. we got beautiful realizations of what the universe looked like, but we realized, look, if we want to get individual galaxies that look like real galaxies, we need to not ignore the complex physics, the normal matter, what we call baryonic physics. That means you need to take into account how gas moves. And gas is basically a fluid. And that means you can heat it up, you can cool it down. Yes, it feels gravity, but it also feels friction. It feels viscosity, just like any fluid does. And the physics gets a lot more complicated when you start to put in the laws of fluids rather than just the inverse square law. But people realize, look, if we ever want to do this, we're going to have to bite the bullet and do it. And yeah, like I said just a few minutes ago, viscosity is not complicated in the sense that it is taught in A levels. Even if you don't do the mathematics, clearly if you've got a cup of water and you pour it, and you've got a cup of treacle and you pour it, it's going to slosh around a lot differently. They are both fluids. They move differently because of the different viscosity. So it's simple in some sense, but actually capturing that inside of a computer is really challenging. So what we and other groups have been doing is taking different tools, hydrodynamical tools, the laws of fluids. We saw a little bit of that in Manisha's talk as well. And that's what we've done. We let 85% of the particles in our simulation be dark matter. They only feel the inverse square law. And then 15% of the particles, yes, they feel the inverse square law, but they also feel viscosity. They behave like a fluid. It's the same sort of techniques that are used in so many different areas, from computational biomedical physics, the design of artificial hearts, through to aerospace engineering, automotive engineering. Many of them use exactly the same techniques that we use in astrophysics. This is why there's a lot of crosstalk between our disciplines in terms of career paths. So that's what we did. Stuck 15% of the particles in there and let them feel the laws of fluids. And the hope was that we would get things that look like spiral galaxies, like the Milky Way, late-type spirals, that have nice thin disks with little bulges and showing nice spiral arms, the sorts of things that we associate with late-type spirals. That was what the hope was. First people to actually do this, so this field's only been around for about 30 years or so. So if you look in the early to mid-90s, you are getting things that start to look like spirals in some sense, or disks. They don't look like the Milky Way. They're not really pretty looking. There's no spiral arms. They're not thin disks. But if I look at this thing face on, and then I turn it sideways, yeah, it's squished. It is a disk. These stars are rotating around, just like they do in the Milky Way. But it's very short. I mean, it's a very stubby, thick disk rather than anything that looks like a real Milky Way. But at least you're starting to get things, when you put the laws of fluids in, at least in the way they were done 25, 30 years ago, you were starting to get things that at least resembled a little bit or behaved somewhat like spiral galaxies. And you could go forward into the early 2000s, mid-2000s, computational techniques got cleverer, hardware got cleverer, but you still had ultimately the same problem. You've got gigantic amount of starlight piled up in the center, and then these little disks that are floating around still don't really look like spiral galaxies. And this is only sort of 15 years ago. We still didn't have anything inside of a computer that looked like a real spiral galaxy. Now, we didn't invent this. Other people realized, look, when you're treating these fluids, you have to make some decision about how you're going to heat up the fluid or the gas, the interstellar medium, and how you're going to cool it down again. And there are different heating sources. Like I said, stars explode. They go supernova, and they dump an enormous amount of energy. If you like energy units of joules, 10 to the 44. It's a crazy big number. So every exploding star, in the Milky Way, one goes off every 10 years or so. It's the equivalent of this many of the most powerful nuclear weapons that have ever gone off on Earth. So you've got an enormous energy reservoir to play with, and you as a simulator has to make a decision. Look, when a star explodes, what am I going to do with that energy? Do I let it radiate away and do nothing? Do I let it push gas around? Do I make bubbles? Do I heat up the gas? These are all decisions that you have to make when you are doing these sorts of simulations. And what was happening was too much of the gas was piling up in the center. So yes, you could still get a disk forming, but you could see in those previous pictures a big bright spot in the center. Gas was still, despite what we were doing with playing with the energy of exploding stars, it wasn't enough. Gas was still flowing its way down to the inner part of the galaxy where it was forming lots and lots and lots of stars. So they just didn't look anything like the Milky Way, even if they were sort of disk-like. The secret was all of that work that was done up until sort of 10 years ago when we got involved with this was just using the energy from exploding stars. Because the thought was, look, they create so much energy. You know, a star like the sun doesn't create, there's not a whole lot of energy associated with a star like the sun, so let's ignore that. Or even heavier stars, they are blowing these winds, but the belief was they don't really influence things. As soon as that star goes supernova, it just blows away anything else that's been done beforehand. So all of the work through the 2000s just ignored what happens before a star explodes, at least those who are doing computer simulations. But these stars, and while there may not be lots and lots of them out there, stars that are heavier than 20 times the mass of the sun, the sorts of stars that explode as supernova, they do deposit a lot of energy into the surrounding interstellar medium. That bubble nebula is not only just making a pretty picture, but it's heating up and making the interstellar medium turbulent. And there's a lot of energy in there, and the gory details don't really matter, and the units don't really matter. This is basically how much energy is being generated as a function of time. And this is 1 million years, and well, you can't see it over here, it's 10 million years. And here's, after a few million years, these stars start to explode, and you get energy being deposited by supernova into the surrounding interstellar medium. And that's what everyone was doing at the time. They just used that energy that comes from exploding stars. This is simple work that was done, 30 years ago by Klaus Leiterer showing, but in fact, before that star ever explodes, these stars ever explode, they are dumping a lot of energy into the surrounding interstellar medium. And it was being ignored. And so that's where we came into play. Stars that are heavier than 20 times or so the mass of the sun, they can deposit, a comparable, maybe not exactly the same amount, but within a factor of 10, the same amount of energy into the surrounding gas as an exploding star. And you neglect that at your own peril. For a lot of the reasons that I said just a few minutes ago, these things drive bubbles, they create empty space before a star ever explodes. So when it does explode, it doesn't waste its energy trying to push its way out of that dense region. It's able to influence things on a much larger scale because you've created these bubbles, these voids, these empty regions before the star actually explodes. And so we implemented that inside of our simulations in a series of papers during that period of time in the early 2010s. And we started to get simulations here on the bottom that actually, for the first time, actually look like real spirals. I mean, they're not perfect, and they all have their little flaws. But this was the first time we got things that looked like late-type spirals with small bulges, thin disks. And the secret all came down to stellar winds, the pre-supernova stellar winds that heat up, make the interstellar medium turbulent, drive big bubbles before the stars ever explode. In retrospect, it seems really simple. But all of the simulators at that point in time just could not believe that stellar winds could actually play such an important role on a large galactic scale. And so we're at a point now where I can put up a panel like that, which is half real and half fake galaxies. And it's actually, unless you have a favorite galaxy in mind, you can't really tell anymore which ones are fake and which ones are real. And I can go just a little bit deeper on this. Here's what would happen if I ignore the stellar winds and I just use supernovae. I run a couple of simulations. This is looking at a disk galaxy face on. Hard to see the colors, but this is just the gas. And if I turned it sideways, you would believe me, it's a disk galaxy. It's a nice thin little disk. The gas is moving around in nice counterclockwise orbits there. And you can see hints of little spiral arms and things there. So it does look, with a cursory glance like a real galaxy. But in fact, if you go in and measure in detail what the structure of this thing looks like, it's what we call too much power on small scales. Everything's wound up too tight, if you like. So if I measure the structure of that interstellar medium, we use this term called power. It's all too compact. If I run the exact same simulation and I put stellar winds in, then you get these sorts of things where it's still a spiral galaxy. If I turn it sideways, it looks thin. Everything is rotating around counterclockwise. But now you can see the spiral arms have sort of opened up a whole lot more. And if I measure the power, it actually is, some of it is on small scale, some of it's on large scale. It actually matches what you see in nature when we look at pictures of external galaxies as well. And again, it's maybe quantifying a little bit what you could see with your eyes, that we had these pretty galaxies that looked real when we put stellar winds in. This is actually quantifying it a little bit more. And also saved one of the great mysteries, and these are all sort of interconnected. I mentioned right at the beginning something called overcooling. If I don't heat up the gas had a tendency to funnel in and fall into the center of the galaxy where it gets dense, and it formed all of its stars in the inner part of the galaxy. And you also form too many of them. If I went out in nature and looked at thousands and millions of galaxies and made a plot of how heavy the entire galaxy is versus what is the mass in starlight, this gray thing that goes across here. So a typical galaxy that weighs 10 billion times heavier than the sun might typically have maybe a million of that 10 billion would be tied up in stars. The vast majority of it is dark matter. And as you go to heavier objects, you can see something that weighs 10 to the 12 solar masses, really heavy, a trillion times heavier than the sun, would have about 10 billion of that 10 to the 12 would be in stars. So there's this observational trend. All of the simulations, again, that were run prior to sort of 2011 all sit here. Not only do they not have the right shape, they actually form way too many stars. So if we run a simulation of a galaxy that weighs 10 billion times the sun, it was forming 100 million solar masses of stars when it should have been down here with a few million. So again, if you only include energy from exploding stars, you get the wrong shapes. You don't get things that look like late-type spirals like the Milky Way. And you form way too many stars compared to what you actually observe in nature. Again, when you put in the stellar winds and allow that to heat up the gas and make it more turbulent, you're actually able to get galaxies that start to sit right down on the observational data without doing any playing around or tweaking things. Don't worry, this is the exact same thing I showed you just a second ago, and this is what happens when I run a simulation with just supernova. Again, I form way too many stars compared to that red band. These are a bunch of simulations where we've not tried to fit them onto the data, but when we take into account stellar winds, all of the simulations sit right on top of the observational data. So this has been a fantastic result and has driven a lot of the work that we've done over the last 10 years. So just to wrap up on two things in the last, 10 minutes. So I hopefully have convinced you that the heliopause around the sun plays an important role in protecting us from cosmic rays that could otherwise make the development of life challenging. I've talked about how the local bubble gets shaped and how both stellar winds and supernovas shape and sculpt the interstellar medium as a whole and have solved this massive problem that drove a lot of extragalactic astronomers, this overcooling problem. But they're more than just that. They are important for the development of life in the sense that most of the chemical elements come from stars of different masses. This is one way of looking at a periodic table, an astronomical periodic table, and again, the gory details don't matter. The different colors tell you the different types of stars that are responsible for the different chemical elements. And what you can see is for lower mass stars, the ones that are a few times heavier than the sun, they split them up kind of between isolated low mass stars that form 2/3 of the carbon and yttrium and various other things, and then low mass stars that are in binary systems that explode as supernova. So they're separated, but massive stars, they just color code, again, one fell swoop, everything is green. But again, not all chemical elements come from the explosion process. Chemical elements get pushed out along with the winds before the star ever explodes as well. So it would be better if they didn't use a single color of green, say, the third of the carbon that comes from high mass stars. It doesn't tell you how much came prior to the explosion in the wind phase and how much came during the explosion phase. So you'd like to see it broken down a little bit more. And so coming back to where we started, which is kind of ignoring supernova and just looking at the role before the star explodes. This is stars of different masses and the fraction that gets ejected in different forms. These are for stars that have a metal content similar to the sun. So stars, say, in this range, 10 to 20 times heavier than the sun. There is a leftover supernova remnant, maybe a neutron star, maybe a black hole. But everything here is kind of white. You get the supernova drives, it creates carbon, it creates oxygen, lots of these other chemical elements. So these stars, 12, 15, 20, 25, it is true. They are largely, those chemical elements are coming from the explosion process. But as you move beyond 20 to 25 solar masses, you see this big shaded region. So stars that are heavier than 25 do blow an enormous amount of carbon and oxygen and helium, and there's other elements hidden underneath that in that label there. And in fact, for stars that are 25, 40, 60, 85, 100 solar masses, yes, they are rare. There's not lots and lots of them out there. But the vast majority of the carbon, the oxygen, and a lot of other chemical elements come during that pre-supernova phase, not during the supernova phase. And it's just a quirk of the way the field has gone that these always get swept up together rather than separated. But that's just sort of one way of showing that these pre-supernova winds, these stellar winds, really are important contributors of the fundamental building blocks of life, carbon and oxygen. And you can work your way through all kinds of different chemical elements, like fluorine, for example. This is a ratio of fluorine to oxygen for a bunch of different stars. If I run a model and I ignore the fluorine that comes before the star ever explodes, I get the solid curve down here. It underproduces fluorine by a factor of 2. Exploding stars, yes, they do contribute fluorine, but you miss at least a factor of 2 of the fluorine in the universe if you ignore the pre-supernova stellar winds. When I put in the pre-supernova winds, I get a good match to the observations. One can do this by working through different chemical elements and finding how much comes from the explosion process, how much comes from the stellar wind process. And yes, the majority are driven mostly by the explosion process, but there are lots of important chemical elements like carbon, like oxygen, like fluorine, that do have a significant component that comes from these stellar winds that have this other benefit of sculpting the interstellar medium. And this is the last one I'm going to end on. I've just got a couple slides, and then we'll be done. And it's come back to where we started from, which was the local, the solar system, the solar neighborhood. Some of you, this is a subset of a few slides that I've used, and I've given a talk on colonizing Mars and whether we're going to do it or not. There's lots of, you can have an entire talk on the challenges in terms of colonizing Mars. The soil is toxic, it's full of perchlorate. There's no food. It's challenging to get water. You've got psychological effects, which is what the astronauts say is the thing that concerns them the most: the isolation, the monotony, temperature. It's like living at the South Pole basically all the time. There's lots of challenges associated with establishing a base, a colony on Mars. How does it link back to stellar winds? Well, Earth has an atmosphere because it has a magnetic field. We've got this beautiful, just like we have this heliopause that protects us from 90% of the cosmic rays that are coming in from outside the solar system. We also have a local magnet. The Earth is a magnetic field. It's got this gigantic magnetic field because of the turbulence in the molten iron core. And it provides this magnetic barrier that stops high energy particles from reaching us. That would again damage DNA, at least anything that was on the surface that was developing. But more importantly, from what I'm talking about here, it would evaporate our atmosphere. This is why Mars doesn't have an atmosphere. It doesn't have a magnetic field. It has the wimpiest of atmospheres, highly toxic, but it's the wimpiest of atmospheres. Basically, the atmosphere has been evaporated because there's no magnetic field. It loses, the best guess, it's a number, it's around 1 kilogram per second of that wimpy little atmosphere that is there, gets blown off by cosmic rays coming from, largely from the sun, because most of them from outside the solar system are being blocked by the heliopause. So even if you could reestablish an atmosphere on Mars, terraforming, whatever the case may be, you only have 10 million years or so before the atmosphere gets evaporated again. So you'd have to have some sort of either reestablish a magnetic field inside, or you have Elon Musk or someone develops a super magnetic shield that sits in orbit that provides that from a satellite perspective. But if you want to reestablish an atmosphere, that's what you have to do. They might ask, well, why does Venus have an atmosphere? It doesn't have a magnetic field. It's a bit of a cheat. When the sun interacts with the upper atmosphere, it actually generates a magnetic field in the atmosphere that protects it. It's not self-generated inside the core the way it is on Earth. So in terms of the development of life and broader questions of life, we do think magnetic fields probably are fundamentally important, because if you need an atmosphere or you want an atmosphere, you've got to have a magnetic field to retain that atmosphere. And it's more than just the atmosphere that you breathe and the damage to DNA on the surface. It's just the general impact of radiation on your body or life as a whole on that planet. If you look at, say, in these units, a CAT scan of your whole body, it's a unit of one, let's say. If you spend a year in space, like Scott Kelly did, that's the equivalent of getting about 100 CAT scans, full-body CAT scans. And, for comparison, standing near Hiroshima when it went off, that's about 200 CAT scans hitting your body in one go. On Mars, traveling to Mars, it's about the equivalent of getting about 1,000 CAT scans to get to Mars. If you want to come back, that's another 1,000 CAT scans. So you've got some radiation issue. And it's not just the trip there and back. The surface, there's no atmosphere. It doesn't protect you. Our atmosphere blocks most of that damaging stuff from reaching us here on the surface. Because you don't have that on Mars, if you want to live on Mars, you really can't live on the surface. You either have to have sort of meter-thick steel walls to protect you, or you go subterranean to protect you from that. It's 1,000 times more damaging to DNA on the surface of Mars than it is on Earth. So thinking back to the title of that talk, the givers and takers of life, this is one of the takers of life, if you like, is that unless you have a magnetic field, even something wimpy like a solar wind makes it very, very difficult for life to ever develop unless you have that protective magnetic barrier that allows you to hold on to the atmosphere. So what's the final scorecard here? Givers of life, well, the heliopause, that solar wind, it does provide protection from interstellar cosmic rays, largely. Not all of them, but the vast majority of them. Voyager has confirmed this. As soon as it crossed that heliopause, the cosmic ray count shot up on the detectors. You could see it. It's not just sort of theory. They've actually got observational evidence of that. They're important for the development, the synthesis of carbon and oxygen and fluorine, and the dispersal of that into the interstellar medium is driven, not entirely, but there's an important contribution that comes from massive stellar winds. It also solved, in my field, it was, while not the total solution, a big missing piece of the puzzle in getting anything that looked like a realistic spiral galaxy came down to implementing stellar winds before they ever exploded into the simulations. And now we do get simulations that actually look like real galaxies. Every other group in the world has picked up on what we've done. Other people had thought about it. We were the first ones to put it into a code. But basically all the codes that are out there now are doing exactly the same thing, heating up the gas, ahead of time before allowing the stars to explode by making use of that pre-supernova energy. And the taker of life, planetary atmosphere evaporation. This is not everything is positive. There has to be a negative, and that is one of the negatives associated with stellar winds. And that's basically everything I wanted to say. I just want to say, for those of you who are near Hull, on May 9th, Pint of Science, which is a UK-wide, worldwide outreach event, which tries to capture the essence of going into the pub and just chatting with people about what it is that you do. We've got a couple of events in Hull, and I know that Leeds is also doing them, and I know some of the staff, postdocs here at Leeds, are doing astro-flavored talks as well, based here in Leeds on May 9th, 10th, and 11th. Those who are Hull-based, 4 of our new PhD students, I've co-opted them. Rather than the grown-ups doing the talks, I've got the new PhD students to give them. So we have the astronomy session for those who are around, and hopefully some of the Hull-based people have already gotten tickets, and hopefully we'll see you on the 9th. But if you don't want to make the trip down the M62, support the Leeds folks here and come to Pint of Science on May 9th, 10th, and 11th here in Leeds. And that's everything. Thank you.
Thank you very much, Brad.
Can I just ask a question?
Go on then.
So, I've seen the shape of the helium sheet has been different. Once it's a teardrop, then it was round, then it was a teardrop again, and then I've even someone, I think it was
Cloverleaf.
folded croissant or something.
Yeah.
And I just wonder, is the shape still theoretical?
Question is about the shape of the
the shape of the
heliosphere.
So the cartoon I showed had you only saw the what looked like a cigar sort of thing. There are observations now, but it's a really challenging observation to do. It does look like it changes. It's not static, and it changes on fairly short time scales. It looks like maybe not daily or anything like that, but on the data that I've looked at over the last decade, and there really is only data from like the last 10 years or so, from maybe a dozen different experiments, and it does look like it has changed, and it does get shaped, as we're moving through the spiral arm, or our little spur of a spiral arm. And so the density is changing. We're moving through the spiral arm relatively, compared to the interstellar medium, about 20-25 kilometers per second. So things are being shaped as we move through the interstellar medium. Any sort of variation in the stellar wind or the solar wind will have an influence as well. But the observations are, from what I've read, are really challenging, because it is a very subtle thing that you are looking for. It is thought to play an important role in possibly explaining. People are really interested in the highest, and I talked about cosmic rays and how many of them actually make it here to Earth. And there's a whole cottage industry about trying to discover the most powerful cosmic ray that is able to make it through the heliopause and make it through our magnetic field and make it to here. And they're not uniformly distributed, it seems. Cosmic rays, well, they don't, sometimes you can associate them with a source, sometimes you can't associate them with a source. But it doesn't seem to be entirely random. And there's some suggestion that by looking at how the distribution of cosmic rays, the detection rate from different places on the sky, that seems to be some evidence maybe that the shape, it's funneling, any sort of high energy cosmic rays that make it are being funneled in through the long end, if you like, of the heliosphere, whatever it's called. So you can infer something about the shape and its role by looking at cosmic ray detection numbers, but you don't see nice, in Manisha's talk, you see these beautiful bow shocks, and you probably see them in Julian's talk as well. You don't get anything that's crystal clear and beautiful looking like you do with that. It's really messy stuff. Cosmic rays get jumbled around all over the place, which is why it is hard sometimes to track them down to where they actually came from. So you get a really blurry sort of image. And I should have put one in, because I looked it up just this morning when I was on the train to look. It doesn't even look, they call it a clover leaf, or four-leaf clover. I can't actually see the four-leaf clover when I look at it. It is clearly not, a nice cigar-shaped cylinder, and it does have structure to it. But it kind of just looks a little blobby. It's just not, it's not well resolved. But yeah, we do have really low resolution pictures of what it looks like, and it does seem to evolve over the last decade, subtly, but it is a probe of what's happening sort of as we move through the spiral arm as well.
And I guess then we're not in a position to be able to look at this on, say, local stars, to be able to look at their shape.
So you actually, it's a little bit easier with, part of the problem with the sun, it's only what we call one solar mass, right, by definition. So it kind of has a pretty wimpy solar wind, so it's kind of a wimpy heliosphere in the grand scheme of things. It's a little bit easier as stars get a little more powerful and are able to sculpt things a little more obviously. And so it is, well, maybe it's not an easy observation, and it wouldn't be, you couldn't do it with a star that was similar to the sun. You'd have to move to a star that was much heavier to see that. But you can pick it out in heavier stars more than you can pick it out in sort of G-type stars like the sun.
Any other questions? Question from the young gentleman right at the back. I'll give you the microphone.
So, a large soap bubble splits into little ones and then merges into one single one. Can stellar wind bubbles merge into a single bubble?
Good question.
Yeah, it's a good question. I'm not sure if Julian's going to show any examples of things like that, interacting bubbles. You have, I guess, the physics that is shaping those bubbles is also a little bit different than the physics, the surface tension that shapes the way soap bubbles, let's say, might interact. So the surface tension shapes how things evolve in the way that you described with the soap bubble effect. Now, these bubbles are not entirely, even though they might look like a soap bubble, there is different physics that is driving them. They are being influenced by solar winds that are blowing them up on the inside. They're being influenced by magnetic fields that are also all around as well. And you got external pressures pushing on them. And so I can't give you a simple answer to that. I'm sure someone can come up with a series of bubble merges that look like exactly the way you described. But the physics would be different. It wouldn't be a surface tension effect. It would be this complex interplay between magnetic fields trying to affect things, the solar wind itself and cosmic rays and things trying to push things out. So it would be a balancing act between a different set of physics than what would happen with soap bubbles that are merging, if you like. Even if you could get one that kind of looked similar by eye, you probably have to tweak the physics to get one that looked like that.
Any other comments, points?
Thank you. Brad, if I could rewind you to an early part of your talk,
Yep.
when you talk about the creation of your model to include supernova explosions, stellar winds, and also dark matter. At what point in your simulations do spiral arms appear, and how stable are they? I'm thinking of density waves where the shape is stable but the constituents are not. What happens in your simulations?
No, you are right, and this one is still a hotly debated topic. You can look at spiral galaxies as a function of look-back time. Go back to redshift 1 or redshift 2 or however far back you feel comfortable with. And you can do counting statistics, how many how many spirals have got 2 arms, 3 arms, 4 arms, and just count them as a function of time. And you find, yeah, there's lots of spiral galaxies back to, let's say, to redshift 1. And so you can interpret that in 2 different ways. Either spiral arms are long-lived, and everything's got a spiral arm, or they're very transient. They come and go, and they come and go, but they come and go on a very rapid time scale. And so you could still count, the counting statistics could be exactly the same, whether they're really long-lived or really short-lived. In our simulations, and they are not the highest of resolution simulations compared to what others are doing now, our spiral arms are not particularly long-lived. They're transient. They come, they go, not on super fast time scales, but they are not long-lived. They don't stay a nice, beautiful spiral for, you know, billions and billions and billions of years. They get disrupted. Both internal and external influences cause them to disrupt and come back and disrupt and come back. But people who are far cleverer than me, who are doing these, you know, the next-gen simulations at much higher resolution, you know, every month a new paper comes out, one which refutes the other one. There's still this hot debate as to whether spiral arms really are long-lived or not. And there's far clever people than I doing these sorts of simulations now who have not been able to resolve this issue. So it's a roundabout way of saying I don't know what the answer is. In ours, we sort of come down in the middle, but I admit our resolution is not as comparable to the super high ones that people are doing now. But even with those, they still don't have the fundamental answer on whether they're long-lived. They are super common, but again, they could be short-lived and just reestablished quickly, or they could be really long-lived. So I don't know what the answer to that one is. It's the right question to ask, though.
Any other questions? Oh, we've got a couple of questions at the top of the lecture theatre, which I keep having to walk up and down to. Well, I'll stay up here.
Hi, thank you for a very interesting talk, Brad. My question is, has any work been done on how, when 2 galaxies interact, what effect that has on these bubbles?
Yeah. There are lots of different ways to approach it, and a lot of the simulations that I showed you were fairly isolated. You know, I chose things that had a history not dissimilar to our Milky Way, which it interacts, you know, the Large Magellanic Clouds are, you know, slowly being disrupted, and there's other dwarfs that are being disrupted. But we haven't had a particularly chaotic, crazy assembly history. It's been pretty boring and quiescent. And so I chose things that, for the ones that I showed you there, that also had pretty boring, quiescent histories. But what I can do is, I can do exactly what you describe. I can look at our simulations at different time steps during their assembly history and look at how the structure of the interstellar medium changes with flybys, with interactions. And you can imagine it really comes down to the intensity of the interaction, really. You know, if it's a hardcore merger, you know, smashing together, yeah, you know, it causes a rightness. If it's more of a gentle flyby, the interaction is a little bit more subtle, and, you know, it can drive gas inwards, outwards. You can pull spiral arms out a little bit, you know, and then there's, you know, everything in between those. Now, something which, again, I've, you know, not been fully truthful about is that we did make, I think, at the time, a big leap forward in including the effects of stellar winds and heating up and making the gas a bit more turbulent before things start to explode. But if you look in our galaxy and I don't know, if you grab some of the interstellar medium of our galaxy and you ask the question, what energy has powered, this interstellar medium? How much of it comes from exploding stars? How much of it comes from magnetic fields? How much of it comes from cosmic rays? Sometimes people talk about equipartition and say, well, look, a third of the interstellar medium's energy comes from exploding stars and massive stars, winds. A third comes from magnetic fields providing energy support. And a third coming from cosmic rays that provide a different heating source. Simulations that I showed, I ignore cosmic rays and I ignore magnetic fields, as 99% of the people who work in this field do, because they're just too hard. So we sweep that complex physics, when we're doing at least galaxy scale simulations, we sweep that complex physics and hide it inside of what we call supernova and stellar winds, even though they're not. The reason I say that is that things like magnetic fields in particular do shape, a lot of the bubbles that we get in our simulations are pretty spherical. But we don't have magnetic fields, depending on the strength of the magnetic field in the disk. If you have a really strong magnetic field that is going sort of vertically through the disk, it acts to sort of squeeze the bubbles. So, the bubbles will kind of be all elongated. So if you looked at it face on, they might look circular, but if you looked at it edge on, they might all be, cigar shaped because they're being squeezed by the magnetic fields. So tracking the, I can say, to first order, we get bubbles that look the right sort of size. But they're probably not the right shape, because even if we have taken into account the influence of flybys from satellites and mergers that are coming in, we have ignored magnetic fields and we have ignored cosmic rays, which probably have a more important effect in shaping the bubble distribution, if you like, than maybe some of the moderate flybys, if you like. So there are people who do much higher resolution simulations with magnetic fields, but maybe simplify the physics of the assembly because you pay a price computationally. If you want to include the magnetic fields, something's got to give. If you want super high resolution, you might not be able to resolve the entire galaxy, so you might only resolve a small region and include magnetic fields. But the field moves, rapidly. It's not so much hardware development, it's software development. As people get cleverer and cleverer, they will capture all of that physics much better than we did.
Thank you.
Well, actually, I had exactly the same question, to be honest. But maybe I've got a different question. Because going back to the heliosphere, and you showed the Voyager probes on there, I guess they kind of deliberately flew in that direction rather than the other one to get out of the heliosphere. And did they give them any useful information on that? Did they agree with the theory of where the edge is, I guess? And did you see what we expect?
Yeah, so let's go back to that picture. I don't know, it's a good question. Did they actually give any thought to the direction? You know what? That cartoon, I guess I would take it with a grain of salt in this sense. Where did it go? It looks like they were, aligned perfectly with the nearest point. But I suspect there's some wiggle room there in terms of, they weren't aimed perfectly to go through the closest point, I would say. In the way that it's drawn there. It's probably a lot more raggedy than it looks like in the cartoon. So it's probably a very misleading plot. I would say that, I hinted at it. It really has shed light, basically as they crossed, the flux of cosmic rays and the density of the plasma on this side of the line versus that side of the line. It goes from low density plasma, boom, all of a sudden it cranks up as it crossed over. And measuring the number of cosmic rays, the cosmic ray flux in the detectors, again, it went from very low values, boom, to much higher values. So it did confirm a lot of what people suggested was going to happen. So it was certainly not what they were designed to do, but it was a ancillary benefit of having done that. But yeah, I would take the positioning probably with a bit of grain of salt
I
there.
think that the trajectory of those was determined by the positions of the planets
That's
that
yeah.
they were visiting. So I don't know if anybody actually considered what direction that was in relation to the movement of the sun.
I'm sure that's okay. I'm not even sure we even had, when these things were launched, what was that, like 7? I've lost track of my decades now, but that was a long time ago. I'm not sure we had any idea at that point in time at all as to the direction. So in retrospect, maybe it was just luck. That's more than anything.
Right, well, I think we'll have to draw a halt to this. Thank you very much to Brad Gibson for talking for so long.
Thank you.
And fielding so many questions. We'll give him a round of applause in a moment. Now. So we're starting here again at 14:30, at 2:30, when we have a talk. It says on my timetable it's a talk about Leeds Astronomical Society, but I don't know who's giving the talk. Does anybody want to? And you are, sir?
I'm Levine, the president.
Mr. Levine, Rod Levine.
Colleague called David Sellers is going to kick us off about the history of the society, which is quite long involved.
Right, David Sellers and Rod Levine are going to be talking after the break, after the lunch break, and later Richard McKim will be talking more about Mars, which we've just been discussing a little bit. Okay, I'll see you all after lunch then. Thank you.